What is manganese? Manganese, it's a naturally occurring mineral. Its symbol chemically is M and a small n, and it's about 1%. It comprises about 1% of the Earth's crust. And you guys in the drinking water supply, you understand concentrations and things of that nature, so milligrams per liter. So if 1% of your water sample was manganese, that would be a concentration of 10,000 milligrams per liter. So that's a pretty big number. So the concentrations that we're going to be talking about are significantly less than that, but just wanted to put that in perspective. How does that get into your waters? Well, it's basically from the erosion of your natural deposits. Wherever you have the manganese underground, it erodes through the groundwater. That's why you guys have it in the groundwater. And you'll also find it in surface waters as well, if you guys do have surface water. One of the things that, if you do have manganese, that you'll realize is you'll also have iron along with that. You do sometimes have manganese by itself or iron by itself, but it's usually found in pairs. And they both can be problematic. And one of the things that's important to note, it is an essential nutrient. It's if you look at your vitamins, if you do take vitamins, it's in there as an ingredient. In the proper amount, it's actually something that the body needs, but in excess, it's actually detrimental to health. And that's the reason that treatment is required. To understand manganese as well, you need to understand the states that the chemical or the mineral can be in. And there's basically two states for manganese itself: the dissolved state and the particulate state, and both of those are comprised as total. So when someone gives you a manganese concentration, they're probably referring to total. And as we get into the presentation later, we'll realize why it's important to know the differences between the dissolved and the particulate state. Dissolved or reduced is the Mn in the +2 state. It can actually pass through, I don't know if you guys do this routinely, but sometimes you have to filter a sample in order to get it to the lab to understand certain parameters. There's filters of 0.45 to 0.22 microns. The dissolved manganese will actually pass through that filter. That's important to note. And I say essentially it's invisible to the naked eye. Granted, we're talking on the atomic scale, you can't really see that. When the manganese is in the +2, you can't really see it until it gets oxidized. And that's the second state, which we're talking about, is particulate or the oxidized. And that's the Mn in the +4 or even in the +3 state. And that doesn't pass through a filter. It's oxidized. We're going to get into that a little bit later, so that it can't pass through a filter, hence the reason a filter can take out that manganese. And that one is visible to the eyes. So when you guys are out in the field or consumers are complaining, hey, my water's dirty, that's what I mean by manganese is visible. It's not that you see the particular atom, it just changes to a state where it can start combining with things and get bigger so that you can't see it. Colloidal is another state of manganese. It's important when it comes to treatment because it makes it very difficult to remove. Colloidal is basically the manganese where it's like bound up or held in place by like an organic, like if you have natural colors in your water, leaves, humics, things of that nature. It just makes it very difficult to remove. We'll get to that later in the presentation. And that one can actually pass through a 0.03 micron filter, so even a smaller filter. So that just kind of tells you that at that state it's very difficult to remove. This is a map of the northern United States. The blue dots and red dots are manganese concentration based on a USGS study of the glacial aquifer, which is in the North United States. They basically determined that the median point was 34 parts per million of manganese, and the blue dots were less than 34, and the red dots were higher than 34. So that was just a midpoint of hundreds of samples that they took in the sample set, and that actually is fairly close to the 50 parts per million micrograms per liter of the secondary maximum contaminant limit that we have. In the right-hand corner, you can see Massachusetts. There's a lot of red dots, hence the reason manganese is very important of a constituent for drinking water in Massachusetts. So why should you care if you have manganese? Well, if you have it in your source and you're not treating for it, you get dirty water complaints. If it's in your distribution system, you'll also get it into your consumers' homes. You know, whether it's the bathtub or it's the faucets where they get their drinking water. Very, very unpalatable. If you do have that, your friend, the phone, will be ringing off the hook. You're gonna lots of consumer complaints. Why else should you care? Well, people have smartphones, and with smartphones, at some point in time, you may actually get a video of a drinking water complaint. This is actually a video that one of my clients received from one of their consumers, basically a manganese-laden water coming out of their bathroom tap. He received an email on this via video. Wasn't too happy about it, but the proof was in the pudding. If I recall correctly, this is basically due to either a fire that happened the prior night or a water main break. So the distribution system got stirred up and hence made it into the people's homes. What about treatment? When is it required? You have the EPA, and you have the MassDEP. For the EPA, back when the regulations started, they actually set a secondary maximum contaminant limit of 0.05 milligrams per liter. And at that time, that was recommended for aesthetics, basically to avoid the issues that we just showed a few photos of. And again, at that time, it was believed to be adequate to protect human health. And again, it was more aesthetics-based. Around 2004, they came out with a drinking water health advisory for manganese. The cover of the EPA document is on there to the right. And in that report, they found out that high manganese concentrations could actually affect your nervous system. And in particular, children and infants, were recommended to not consume waters or anything with manganese that had a concentration of greater than 0.3 milligrams manganese per liter. And in particular, the baby formula is actually supplemented with manganese, so it already has manganese, and if you add it with a manganese-laden water, it's going to be higher than they desire, or bad for their health. From the DEP's perspective, they have the Office of Research Standards guideline, and they have a level of 0.05 milligrams of manganese per liter on that. If you do have manganese in your distribution system, or I should say in your raw water, your treated water, between 0.05 to 0.3, you will have to consult with your local MassDEP office on what you're going to have to do there. The regulations are based such that if it's over 0.3, you will probably have to remove it, and it's based on the type of system that you have. And in regards to manganese, the DEP obviously has been asking you guys, I believe, to put information in the consumer confidence reports, some language about manganese and its concerns, so you guys have probably been dealing with that as well. Once you know you have manganese, you probably want to know how much you have, and you want to know relatively quickly. You can take a sample and send it to the lab, but that obviously takes time and it can be costly, and sometimes you just want to have your results pretty quickly. Over here on the right, from the top to the bottom, we have 3 units, going from simple to more complex and cheaper to more expensive. The one on the top right is basically a colorimetric wheel, a pretty simple apparatus. I've seen some of these in pump stations that I've been in the past. Maybe that's what you guys use. The one in the middle is a Hawk. It's a DR890. It's a spectrophotometer. It's about $1,000. It can give you instantaneous results in the field, pretty accurate. It's actually something that we have in our office when we come out to help you guys out in regards to iron and manganese issues. And the one on the bottom right is basically a lab type setup. If you have a treatment plant, you might have one of these, and it doesn't just do iron and manganese, but it does more parameters, so it's much more expensive, in the several thousands of dollars. So basically, if you do have manganese issues or iron issues, you do want to have some field or office equipment. It is easy to use, and it gives you those fast results to react to the consumers and any issues that you have. Some of the things you want to be aware of is there are low-range reagents and high-range reagents. So it's not just one reagent which will tell you how much manganese you have in your water. Sometimes if you're on that lower range and you use the high-range reagent, you might get the wrong number because it's so low that the high range is looking for a much bigger number, so it's not that accurate. And then if you have a higher level of manganese and you're using a low-range reagent, it's just going to tell you it's max level, and you're going to get a false reading until you start doing some dilutions, and that can get a little more complicated. So it's important to have an idea of roughly where the manganese is, so that you can do that appropriately. And also, as I stated before, there's those different states of manganese. You have the dissolved state as well as the particulate state. So you want to be able to have maybe a filter apparatus or something in the field that will allow you to differentiate between the two, because if you do have a problem, it's going to help you identify what the source of that problem is based on the state. What are the options in regards to manganese treatment? Well, you have source management, you have sequestration, and then you have ultimate removal of the manganese. For source management, you just don't want to use it. If you have the ability to turn something else on, great. You can also blend it with other sources to try to get that manganese down, assuming MassDEP allows you to do it. You can also look for an additional source if you have unlimited budget, but with SWMI and other regulations down the line, it's going to be a little more difficult. But you do need to be careful if you're just going to try to let that manganese kind of go away, and we'll get into that in another slide later. For sequestration, basically, you want to do that when you have lower levels of manganese. As we talked about before, DEP won't let you do anything if you have more than one. And sequestration, we'll get into it a little bit more later, but it's a temporary binding of that manganese particle. It just kind of keeps it in solution so people can't see it for a certain period of time.
And the benefit of that is it's significantly less cost than having to build, say, a water treatment plant. In regards to removal, it's preferential when you have a lot of manganese in the water, as well as required when you have more than 1 milligram per liter. It's the physical removal of the problem, so you don't have it after the fact. You send that water out into your distribution system. However, it comes at the higher cost. The better solutions typically aren't necessarily the cheapest.
There's a couple of chemicals that the DEP is okay with in regards to sequestering manganese or iron in your distribution system. One of the first ones is a polyphosphate. This actually binds with manganese as well as the iron, and it breaks down slowly, and that's what I was saying in regards to the fact that it's a temporary solution.
And there's various recipes per manufacturer, so it's a polyphosphate, but it's a little bit of this and a little bit of that. They don't really tell you what's in there, so you've taken their word that it's NSF 61 and it's certified and all of that, but you don't really know exactly what the huge recipe is going into there. On MassDEP's end of things, the Office of Research and Standards will require an evaluation if the manganese is between 0.3 to 1.0. They're not just going to let you do it carte blanche. They do limit the dose of your phosphate to 4 milligrams per liter to basically keep nutrients out of your distribution system, because that's problematic. And in regards to the design for that, you need to inject your polyphosphate prior to the oxidants with as much time as possible. Otherwise, the manganese will get oxidized and the polyphosphate won't be as effective as it could be. And one of the things that you also need to do is, because phosphate can be a food source, you do need to maintain a higher chlorine residual in your distribution system just to maintain that disinfection. The other product that you could use would be a sodium silicate. Similar to the polyphosphate, that also binds with the manganese, kind of holds it into solution. It also breaks down slowly.
Because this one is often referred to as the Band-Aid approach, because it just kind of buys you some time.
And there are also various recipes per the manufacturers for that as well. And similar to the polyphosphates, the MassDEP does have their guidelines and requirements for the silicates as well. And it's basically only applicable up to a 1 milligram per liter concentration of iron and manganese. They limit the dose to 20 milligrams per liter, 60 total for silica. And for this one here, you have to inject it with or just prior to your oxidant, a little different than the polyphosphate for it to work properly. You also need to maintain a satisfactory chlorine residual in your distribution system. And one of the things that the MassDEP has in their guidelines is that on-site piloting is required for the sodium silicates to be used. The least capital is required. You're basically talking about metering pumps, some day tanks, and some chemical. It's pretty simple stuff. You're not talking about a major treatment plant. Things to be concerned about, it is temporary. You know, it is going to break down over time. Detention time in your distribution system. I mean, there's water in your system that are in there for days, if not longer. So the detention time of that sequestrant may not be as effective the longer it stays in your distribution system. pH is also one of the things that can impact the efficacy of the long-lasting residual, as well as hot water heaters. The hotter something is, usually the faster the reaction goes. So you may break that down in your consumer's water heaters quicker than you'd like. And distribution system instability, whether you have varied groundwater sources that are being treated a little differently, even though you got a couple of wells right next to each other, they're not necessarily the exact same water quality. And there are some water supplies that also have surface water as well as groundwater, and those mixing situations can also create disruptions for sequestration. And it adds nutrients to the distribution system, specifically the phosphates. You know, phosphate is something that organisms want to grow, and that'll impact anybody that has a wastewater treatment plant in their system that's actually discharging to a river. There's phosphate limits, and it's getting tighter and tighter. So if you do think about using a sequestrant, you do want to talk to your wastewater department just to make sure that they're on board with what those secondary impacts may be. And another word of caution with polyphosphates is, if you're doing things for corrosion control, an overdose can actually be problematic for those coatings that have formed to allow you to pass your lead and copper rule samples.
Here we actually have an example of sequestration, and it was a project or several projects that I worked on with the Devens Water Department in Massachusetts. It was actually the old Fort Devens facility, which had been transferred over and tried to make into a community. They had significant companies and growth that was anticipated back in the late 2000s. So we were hired upon to evaluate the system and do some upgrades to allow them to provide the water that was required. There are several wells in the system, and some of them were upgraded to additional capacity, as well as with modernized chemical feed facilities. And on the right, you can actually see at the top one of the facilities. It's a brand new building with the chem feed processes inside, and the photo on the bottom is actually a photo of the process which we upgraded in there. A little bit more just on the project itself, why we did this. They basically had varying concentrations of manganese in their drinking water. Several sources, and the concentrations range from the non-detect to about quarter of a part, 0.25 milligrams per liter, as well as some iron. They historically had been sequestering. They were doing it for the iron and the manganese, the lower concentrations, as well as for corrosion control. So it was selected since the levels were low enough that sequestration could be a potential solution. We stuck with that, and a blended phosphate, which could do the sequestration as well as the corrosion control, was selected as the chemical. There were 3 wells that were upgraded with these types of facilities, and basically one of them went online in 2008, 2009, 2010. The bottom photo over there, kind of in the middle of the photo, you can see some barrels, and behind that there's a day tank, and that was in essence the phosphate system. Just a couple of barrels, a day tank, a drum pump, some chemical feed pipes and pumps, and then pumping it up into the injection point. And the facility was constructed in whole. It wasn't just the addition of the phosphate system itself, but looking at the numbers from the contractors, it was about $30,000 per installation to do a sequestration upgrade. So now we can get into the removal process for manganese, and there's several different media and ways to do this. Some of them, basically the more prevalent ones, are oxide coated media, and you guys might have heard of like green sand or green sand plus. These are pressure filters that actually remove the manganese. There's proprietary media as well. Companies like Lane with their Lanox, PureFlow with their PM medias, and I think Tonka with the Ironman media have their own special oxide coated media for this process. And then you have pyrolusite media as well, which is basically like a solid manganese dioxide, and I believe that's what is on the right. It's a darker granular media. And as I talk about these, the room's kind of big, but I do have a bunch of samples of the media that I have used in the past, and feel free to come up at the intermission point if you guys want to take a look at some of these. It's pretty neat, and some of them are heavy and some of them are more dense, so you'll be able to see the differences between the media here. Some of the other ways to remove manganese include ion exchange, like a water softener, more for the smaller type of installations. Biological filters, which is contrary to what we do. We try to kill the bugs, so we send out clean drinking water, but the biological filters actually use the iron and the manganese bacteria to remove the iron and the manganese prior to sending it to the distribution system. And then ultimately all the way going to membrane filtration, which is a much higher end type of a treatment for manganese removal. Here we have a simplified formula for manganese. So basically on the left hand side you have your Mn+2, which is basically your dissolve, and it's also referred to as reduced or manganese. You mix that in with an oxidant such as like a chlorine or air, and we'll get into some of the other oxidants later. And that'll transfer it, basically remove a couple of the electrons and bring it into the particulate or the oxidized or the manganic state to the manganese +4 state, so that it's actually removable. A word of caution in regards to some of those do-nothing scenarios or the blending scenarios, because one of the things that you need to know about is aeration in particular will slowly oxidize your iron and your manganese. So, sometimes pumping can cause this just through all the turbulence, things of that nature going on into the system and in the wellhead. Disinfection itself, chlorine is an oxidant, whether you're using chlorine gas or hypochlorite, whatever you guys are using, that is an oxidant. And if you chlorinate your water and you have iron and manganese in there, particular manganese, you will oxidize it, and it's going to turn into that black mess that you guys saw earlier. And then higher pHs as well. If you guys do corrosion control, which I'm sure most of you are, if not all, The higher the pH, the faster the manganese will oxidize. So if you're doing aeration or disinfection and you're raising the pH, you're only potentially making the problem worse or quicker in regards to the distribution system. And worthy to note is, even if you're under that secondary maximum contaminant limit, or the ORSGL for DEP of the 0.05, that is low, but even if you do pump that out into your distribution system, over time that manganese will collect, it's going to settle out, it will oxidize, and during like a water main break or a fire or some sort of a seasonal, flow change, all of a sudden people start filling up their pools and watering their lawns, things of that nature, you're going to stir that up, and your friend, the phone's going to come back. You're probably going to get a lot of phone calls. And this here is, it's basically the stoichiometry. And what stoichiometry is basically how much mass of, say, an oxidant, which we have on the left-hand side of the slides, do you need per unit mass of manganese. So the most common oxidants that we use on the drinking water is aeration, ozone, chlorine. Here it's hypochlorite, permanganate, and chlorine dioxide, top to bottom. And on the right, you have the stoichiometry. So basically, for aeration, theoretically, if you had 1 milligram per 1 milligram of manganese in your water, you would need about 0.2 milligrams of oxygen to oxidize that. And going down the list for ozone, you need about 0.88 milligrams per milligram of manganese, chlorine 1.3, permanganate 1.92, and all the way down to chlorine dioxide at 2.45. Some of you might be thinking, wow, I thought chlorine dioxide and chlorine were very strong oxidants, much better than air and things of that nature. And it is true, they are a little more effective at oxidizing manganese. But one of the things that the stoichiometry doesn't tell you is pH effects and just time effects. The aeration, you only need 0.29 milligrams per liter of oxygen per milligram of manganese, but that's going to take hours to have its effect and actually oxidize the manganese. If you use hypochlorite or ozone or chlorine dioxide, I mean it'll oxidize the manganese instantaneously. It's a much faster chemical, but you do need a little bit more of it. So it's the yin and the yang, a little bit for a longer time or a lot for a shorter period of time. It just comes down to what you need. Some of the oxidants are actually very strong as well. We've run into this in piloting. Specifically, you have ozone. You want to oxidize your manganese with ozone. Some clients have ozone. They want to use ozone. And one of the cautions with ozone is you can actually over-oxidize your manganese to the point where you create permanganate. You create that purple water. So it's a tricky chemical or oxidant to work with. And you do find iron with your manganese. So I wanted to at least include the stoichiometry for your iron as well. And as you can see, aeration at the top, all the way down to chlorine dioxide at the bottom. It's about half of the amount needed with iron as it was with manganese. And the one on the bottom for chlorine dioxide, we have 0.24 and then 1.2. Those are actually two numbers that came from two reputable drinking water AWWA publications. I'm pretty sure the 1.2 is the correct number, but I wanted to throw both of those on there just to be complete. And I did check the books, and there were no errata sheets or anything, so it's just, I wanted to make sure that you guys had the numbers, but I'm 99.99% positive it's the 1.2 on that one there. And then ultimately, just to go back to the aeration for manganese, it took a lot of time, and you needed a high pH for the aeration to work. Aeration for iron, it can almost happen in front of your eyes. If you had a cup of water, you take it out of your well, you just set it up on the counter, you can see the iron start to discolor and settle. I wanted to go over some of the removal examples for the manganese removal. The first one for the pressure media filtration is actually in the Littleton Water Department, the town where I live in. They basically had one particular source that had lost significant capacity over time. It was found out to be due to high concentrations of iron and manganese. We went in with a well replacement program and ended up recommending 3 replacement wells to gain some additional pumping capacity for them, but to also reduce the velocities on the wells to decrease fouling of the well streams with the iron and the manganese. And what we did is we recommended 3 replacement wells with an installed capacity of 285 with the ability to go up to 500 in the future should they need the additional flow rate. And the water was actually of decent quality, but it did have manganese and iron in it. The manganese in the 3 wells ranged from about 0.15 to 0.3. And over time, if they were going to go from that 285 to say like the 500 gallon per minute flow rate, I think most of you guys know is the harder you pump your wells and the longer you pump them, the more likely the iron and the manganese is going to go up and water quality degrade. So they, in a proactive approach, wanted to look at removal of the iron and the manganese from the wells, and at that time, a few years back, MassDEP was starting to really start talking about manganese, so they wanted to be proactive in that sense to remove it before the regulation actually hit. So what we did is we piloted the worst of the 3 wells just to kind of bracket that, and we ultimately realized that the Green Sand Plus worked really well. We ended up with 3 6.5-foot pressure filters rated for the 285 gallon per minute initial flow rate with expandability to 500 in the future, and they were sized such that they could take the 500 gallons per minute at the current state. So in the future, all they'll need to do is just put more water through the facility and don't do any other upgrades. Chlorine was the only oxidant used as part of the process. One of the things that a lot of people think about is, hey, I have green sand, I have to use permanganate. That's not true. You don't have to use permanganate. Sometimes your water quality will dictate that use. But for Littleton's sake, they only needed chlorine. It's discussed as described as the catalytic oxidation mode, the CO mode, where you basically need to just have enough chlorine prior to the filter. So you oxidize the manganese, carry a residual through the filter, and come out of the filter at about 0.5, and that maintains the capacity of the filter itself to remove any additional manganese in the water. They also had a backwash recovery and recycle process to increase the throughput of the facility, and what that is basically every so many hours you need to backwash your filters, and rather than taking that dirty backwash water and just letting it go into like the ground or some sort of an infiltration lagoon, we actually had designed a couple of tanks to hold that water, allow it to settle, and then that clarified water was recycled to the head of the plant to basically increase the production through the facility. The facility was online in April of last year at a cost of just about $3.3 million. And just on the photos, the top photos just during construction, with the 3 filters in place before the walls had been put up, and almost from the same perspective, an interior photo once the facility was probably 99% complete. You guys can see all the face piping and things of that nature. For the Rye Water District, what was going on is they had a couple of bedrock wells that were high in manganese as well as iron, and the level of manganese was about 0.1 milligrams per liter. And through piloting, it was actually discovered that the manganese and the iron was actually sequestered naturally by the organics. And one of the things that I was describing earlier was, colloidal iron and colloidal manganese, and if you have color in your water, things of that nature that make it difficult to remove or filter, and that's ultimately what the Rye Water District had. And during piloting, they tried to do the high rate medias, because the high rate media means you can push a lot more water through per square foot, so your filters get smaller, and it tends to be a more economical process. However, they needed to use a coagulant in order to attack that color so that they could get at that manganese and the iron and remove it successfully. But when you use a coagulant in a pressure filter, you're actually pushing less water through it because the filter gets gummed up pretty quick and you're backwashing it more often, which will increase your O&M cost. So at that point in time, I understand that they decided to look at the biological process, which is referred to as the Ferrigure and the Magnesure process. And from what I understand, it's a media that pretty much only needs a stable pH and oxygen in order to allow the naturally occurring bacteria that you would find in your wells that eat the iron and the manganese and form those slime layers to actually remove the iron and the manganese from that water. And ultimately, following some successful piloting, they did decide to proceed with that process. The picture on the right, obviously, the project has not proceeded yet. That's a sample photo of what a filtration process of this nature could look like. Again, just a pressure filter with a bunch of valves and piping to make the water go where it needs to go. The design would ultimately be 3 8-foot diameter pressure filters. They would only need pH adjustments and the addition of dissolved oxygen to feed the process. And the capacity of the facility would be 1 MGD with ultimately 1 redundant unit. And the reduced footprint, with the ultimate goal of having a reduced footprint in residuals from that process, because from what I understand, that process is actually backwashed less frequently, so you have less waste coming off of that, assuming it works properly. The facility is currently in design, and the estimate for that facility would be about $6 million. I have a couple of membranes. If you folks are interested in looking at them, we're going to have two different membranes that we're going to talk about here. Hadley, Mass, several years ago, back when perchlorate was the I guess soup du jour at the time, when that came up in regards to the regulatory environment, they had their Mount Warner wells. They had a couple that detected perchlorate in two of them, and one of them was above the limit so that they could not use it, and the other one was below the limit but starting to approach the limit where they couldn't use it. Hadley was lucky enough that they also had two other large producing wells in another part of town, referred to as the Callahan wells. But the only problem with those was that they had manganese in the water. It was about 0.6 milligrams per liter. And previously to that, they had been using a sequestrant with the sources, and it was a high number, and they were using, I think, a phosphate, and they were having coliform issues out in the distribution system. So they stopped using the Callahan wells and went to the Mount Warner wells. One of the goals that the town wanted was, to have a centralized treatment facility for the entire town, which had future regulatory compliance, not just for that contaminant, but also for the future, what could be anticipated, as well as expandability for the town as it grew. So what we did is we piloted the green sand medias to bracket the cost-effective pressure filters, and also membrane filtration, because that's something that they were very, very interested in. And ultimately, through piloting, ultrafiltration worked very well, and based on their desires, that was the one that was selected to proceed with. Two xenon ultrafiltration trains, the 1000 series membrane. This smaller one here, it's a less robust membrane. The pH was actually over 7 naturally, so they didn't need any pH adjustment. And the permanganate oxidation was sufficient to oxidize all the manganese so that the membrane filters could remove it satisfactorily. The design capacity installed was for 2 MGD, and they basically had room to add additional membranes in the tanks to upgrade that to 3 MGD in the future should they need it. They actually had a very high recovery, because the membranes, you can actually recycle the water through another set of membranes to get even more capacity back. So basically their recovery was 99.5%. So if you think about it, if you were treating 1,000 gallons, only 5 gallons went to disposal for say, like from the backwashing process. Like a green sand plant, if you're lucky, about 85%. If you're not recycling, 15% goes to disposal. So 1/3 what you would traditionally get from a standard facility of that nature. That one went online several years ago in 2007. The cost at that time was $5.1 million. And that one was actually drinking water SRF funded. The photos that I do have there, the one that's on the top right is basically just a view looking through the garage door. In the front, you can kind of see one of the tanks for the membranes. That's actually a recycle system, the one that takes the backwash and recycles it further. And the building on the bottom, pretty simple, but it's actually a fairly large building, and it was actually made to resemble a barn in a historical neighborhood where they actually still grew tobacco. The siding was actually laid out vertically as opposed to horizontally, because if you've ever seen a tobacco barn, when it comes time after the harvest, they hang the tobacco and they open them up, so it's slatted. So that was one of the requirements that they had to do architecturally for the facility. The second membrane filtration project is another fairly local project. It's for the Acton Water District. It was basically for their Kennedy and Marshall sources. They were underutilizing these sources due to significantly elevated manganese. They had iron, and they also had color in the water as well, which made the treatment difficult. The manganese at that time ranged from about 0.4 to well over 1.7 milligrams per liter. So some pretty interesting water. And those two sources accounted for over 25% of the system capacity during the summertime. So it's a source that they had to use. They couldn't just shut it off and have people have plenty of water. So basically they needed to use them in the summer, and when they used them in the summer, they had a lot of consumer complaints. It was a pretty tough water. For that facility there, we piloted multiple medias. We started out on the low range to try to make it economical. We looked at the green sands and the other proprietary medias. We used various oxidants. We had to use coagulants to get the color out of there. And we also looked at membrane filtration. But because the media just really weren't working that well, similar to the rye example, the run times weren't long enough, the oxidation wasn't satisfactory enough so that the treatment could not get removed well enough. Then we transitioned into the membrane filtration process. They also had a xenon ultrafiltration type of system, and they actually used a 500 series, and the 500 series is the one that have it's a much thicker or wider membrane, and that's because it's reinforced. You could actually tie your shoe with this thing and it wouldn't break. The other one, you can just take your fingernail to it and pull it apart. It's pretty not flimsy, I should say, because it's used for treatment, but it's not as strong as, say, the 500 series. And the reason why we had to go with the 500 series is because they're using a coagulant. The coagulant is sticky and it sticks to things, and it makes it significantly harder to remove stuff. So you do need to have a much stronger process to remove that. They also only needed potassium permanganate to oxidize the iron and the manganese. The chlorine had the potential for THM concerns, formation potential, so they decided to stick with the permanganate there and then do the post disinfection with the chlorine. The capacity of this facility was 0.5 MGD with 100% redundancy, and it also had a backwash recovery / recycle process to increase its throughput. This one went online in the September of 2009 at a cost of $5.9 million. And the bottom larger photo is obviously just the exterior of the facility, and the top photo is the two membrane tanks where the membranes are basically submerged and just, hanging in there, removing the iron and the manganese. And you can tell from the top of the tank it's pretty black, so they did have quite the manganese in that water. And the treated water, that if you looked at it and compared it to, say, like a spring water, you wouldn't be able to tell the difference. In another project which I'm working on currently is the town of Bellingham, Mass, for the DPW. Little history there is they had significant total coliform rule violations. They were getting a lot of coliform hits in the distribution system. They decided to start disinfecting on their own to try to take care of that. Then ultimately, I think a year or two after that, their well number 12 was actually triggered by the groundwater rule. So they had to disinfect that source. They had to provide that 4-log viral inactivation. And at that point in time, they decided to pretty much go permanent with chlorine disinfection. And the problem with the chlorine, as we talked about before, is if you have the iron and the manganese in your water and you're not removing it, once you chlorinate it, you do create that problem. And they had significant consumer complaints throughout the distribution system. So at that point in time, we were hired to actually look at their system. We performed an exhaustive study looking at, could they go to new sources? Could they, do interconnections? Could they sequester? Could they treat? And it basically boiled down that the most cost-effective for the solution that they were looking for was treatment for the entire town. So basically, all of their sources are being treated. And it's going to be for iron and manganese as well as the disinfection requirements of the groundwater rule. And I don't know if you guys know, but Bellingham is just one of those long, narrow towns. It's not a circle or a square or anything. It's long. It's pretty extensive. They have sources in the north and they have sources in the south. To do one facility would have required too much piping, too much pumping. It wouldn't have been cost effective, so it was decided to upgrade an existing facility that they had in the north, increase its capacity, and then build them a new facility in the south to remove the iron and the manganese at 2 centralized locations as opposed to just one. What we did for them is we piloted the worst quality source in each region, and by that I mean the one in the north and the one in the south, for the extensive piloting period. And then after that, to keep the piloting economical, we did a shorter pilot study at each of their other sources as a confirmatory pilot, just to make sure that what was going to be recommended would work for others. It was very successful. They decided to stay with Green Sand Plus, which is what they had at the north, and we modeled that for the south as well, and the continued use of chlorine for the oxidation as well as the disinfection for the groundwater rule compliance. Hartford Avenue is the one in the north. The capacity for that one increased from 1.44 MGD to 2.4 MGD, and ultimately we needed to add 2 new pressure filters. I believe they're 11-foot diameter filters, so they're pretty big. In addition to their 4, so they have 6 at that facility. And for Rentham Road in the south, similar capacity, 2.41 MGD with 4 new pressure filters. at that facility. As I stated before, they had several sources. 17 also includes like the satellite wells and things of that nature. So sources, if you want to call it, they probably had 9, but then several of those sources had multiple well points. The facility is currently under construction and should be pretty much done pretty soon. They have an ACO date of March 27th. And the total construction cost for that facility is $11.1 million. About $8 million of that going to the 2 water treatment plants, and about $3 million, just under 3, going to extensive water mains. There were several miles of transmission mains that we had to include in that as well. And that was also drinking water SRF funded. Photos on the right, top right, is just the exterior of their existing Hartford Ave facility. The one just below that is looking down the pipe gallery, or the face piping of the 3 filters on either side. And below that is we have a couple of shots of the newer filters for the Wrentham Road facility, prior to the walls going up, and on the bottom just the construction progress photo of the Wrentham Road facility. Typical implementation steps for a implementation of treatment would require some piloting, as we alluded to. The design, typically have to go through permitting, bidding and construction, the startup, and the commissioning. It is required for most systems. MassDEP does have a policy, it's number 90-04, which talks about what you need to do with piloting, what types of samples you need to do, how long it needs to be. As I said before, most of the systems do need to pilot. There is an exception from what I understand, and you can do online piloting for very small systems, or small systems, like say like a school of some sort, where you don't have the time or the budget to actually do the pilot and then go into design. The DEP has the exception where you can actually install like a proven technology and run it through its proof out period at that point in time. We're actually going to be helping out a small school in the town of Gill with that process. So it's pretty new, so we're looking forward to that, and it's going to be a USDA funded system as well. Once you know that you have to pilot, you do have to submit a pilot study proposal. And typically the pilot study proposal, the DEP's permit number on that one is BRP WS21. And with that, you're asking them to pilot the source. You need to tell them what you're going to be doing, what type of technology you're using, how long it's going to go for, what type of water quality you're going to be collecting, and ultimately what your goal is. Once you do get that approval, you can, perform the piloting. And for manganese and iron, there is a minimum 5-day duration on that, and it's a consecutive duration, so that's kind of the starting point. And throughout piloting, you need to collect water quality data and operations data. Things like your filter run times. How long does it take before you backwash and then need to backwash again? Because if you're backwashing too much or too frequently, it's probably not going to be a good process, because you're going to be wasting theoretically a lot of water. How well is the treatment process working? Is it removing all of the manganese, most of the manganese, some of the manganese? And then you need to look at your chemical dosages as well, because you want to make sure that you're not overdosing or underdosing. So there's a lot of data that needs to be collected during the pilot study. And once you have that, you actually need to put together the report, how it went, how it worked, and how you want to proceed, and submit that to the DEP for their review and approval. And if everything is okay, ultimately you do get the recommendation, to proceed so that you can go into the design stage. The photos on the right that I have there are actually just some shots from the Littleton pilot study that we did a couple years ago. The taller one on the left is actually a shot of the aeration pilot column on the left. They had some low pH concerns, so we actually looked at aeration. That dropped into that white tank, which was then pumped up to the top of that blue tube, which is basically, that's where the iron and the green sand plus column is. You had the anthracite cap and then the green sand within that, and it got filtered out, and basically you got your finished water sample. The top right photo is basically just the 2 pressure gauges that you're watching during the pilot, and one of them is the pressure going into the filter, and the other one is the pressure coming out of the filter. So over time, that differential pressure will grow, and it's one of the triggers that you'll get for your backwashing sequence, ultimately when you need to backwash. And for say like a green sand or green sand plus, green sand plus, typically anywhere between 6 to 8, maybe up to 10 psi is when you get that trigger for the backwash. And then the bottom right photo, that's actually 3. They're called Imhoff cones. You typically use these just to measure, how much sludge you have in your backwash and how quickly it'll settle. And the Littleton wells, they didn't have too much iron or manganese. They had just enough that they wanted to remove it, but you can see a couple of brown dots at the bottom, so it was pretty minimal in regards to the sludge for a typical backwash. So once the DEP gives you the okay, that's when you ultimately go to your design stage. And design, pretty straightforward. You got the preliminary design where you work to get the basics of where you're going to, and then you get the final design where you dot the I's and cross your T's, basically getting it bid ready. And one of the things to note is, you guys are coming from the user side of things, you're operating these things, so if you do need to get a facility built, engage the engineer early on in the preliminary design phase. You guys are going to be operating it for the next 10, 20, 30 years, who knows how long. You need to live with it, so you need to let them know what your preferences are. Everybody has differences and preferences, so it's definitely something that you guys need to voice your opinion on early on in the process to make sure it's captured. Also, during the design phase, you do have to go through permitting. Permitting is one of the things that you have to do locally, whether it's like the planning board or zoning, things of that nature. You're going to have environmental permits, which is more than likely Concom. You guys have wells, you're probably near wetlands, and if that's the case, you do need to do permitting through Concom. You might have MEPA, whether you have endangered species or you're doing a certain flow rate facility, which will trigger one of their review thresholds, things of that nature. As well as on the other regulatory side, specifically the MassDEP, where they have a variety of design approval that needs to be submitted based on, whether you're constructing a facility and what size that is. I listed BRS 23 and 24. 23 is broken down into 23A, B, and C, and that's ultimately if you have a facility which is less than 40,000 gallons per day all the way to just under 1 million, and 24 is if you're 1 million or over. And then one of the things that you need to acknowledge as well is there's various water supply checklists that go along with those permits, and that's for safety in regards to the chemicals that you're adding, KOH, NaOH, your chlorines. And those are small. They're about, maybe 15 to 17 pages each, so it's pretty intensive stuff. And they do need to be submitted as well with the permit. And then once your design is okay and it's approved and MassDEP has authorized you to build the facility, you can go and bid it, and you typically have to go through the central register process, get your bids, evaluate the bids, and ultimately award that project. Construction is typically, obviously, the longest component to any process to the project. It can be anywhere from under a year to maybe a year and a half to more. Once the facility is built satisfactorily, you got to go through your startup process. And in the startup process, you need to check out all the equipment and all the processes. You want to confirm that it's working and it's working well, and that things that are talking to each other to tell the backwash to turn on and the pumps to turn off are actually doing what they need to do. And then you start actually running through some water, pumping it to waste, making sure that the treatability goals are being met. And once you do have that confidence, that's when you call the MassDEP. They do have the formal process of a request for the final inspection. They'll come out, they'll check out the facility, make sure it's built to the standards that they require, and ultimately after that point you'll get the okay to pump into the system and you're ready to go. The picture on the right is just basically the exterior of the Littleton water treatment plant. Actually pretty basic, but I thought it actually ended up looking pretty good for a municipal facility, so kind of proud of that one. Here, this is just an example schedule, which I pulled out from our Littleton project. The bars actually start right around the time after the pilot study report was submitted. The schedule starts in January of 2012, and we did the piloting from January to February and the report into March. We submitted the pilot study report. The first red bar, that was MassDEP's review of the pilot study report. Once we got their okay, we were able to start with the design and the permitting process. The next few bars, some of the green, were basically reviews with the owner. Again, it's very important to get your input during the design process. And then ultimately the next red bar was the design submittal to MassDEP to make sure that the facility was designed in accordance with the regulations. Once we got their approval, we bid the project with the smaller blue bar, and after you award the project, the longer black and the blue bars is basically construction. And Littleton, I believe, took just over a year. It might have been about a year and a couple months to finish it up, start to finish in regards to construction. For a typical project, if you do need to do treatment for manganese, it's not a 1 month or 2 month or even a 1 year process. It actually spreads out into 2, if not up to 3 years. So it's not something that happens overnight. Manganese is definitely something that is problematic. It's going to cause your dirty water complaints. And if you're dealing with dirty water complaints, you are going to have increased O&M costs. And by that, I mean your admin folks having to answer the phone and talk to people and tell them what's going on. You're going to need to react to these types of issues. You're going to need to go out and flush, and potentially, some people might think that flushing is wasting water, even though it helps your system. So you do have that increased O&M cost. And more importantly now, back in the days when people would say, hey, I got iron and manganese in my water, you're able to say, hey, it's it's safe, it's an aesthetic concern. But now you do have the manganese regulation, which is changing and turning that into like a health concern too. So you're going to have that to also educate the public with. And ultimately, in regards to the solutions that you guys have for consideration, we talked about source management is something that you guys might be able to do. If you want, you can look at sequestration, assuming that the levels are where you can have it at, as well as ultimately looking at removal, taking the problem out so that you really don't need to worry about it at the end. It's important to work with your local regulator. Ultimately, once you know you have the issue, to kind of go through some of those options with them, figure out what you can do. And you do want to work with the experienced consultant, because as we talked about, the treatment can be complex and it can be costly as well. You want to make sure you're going down the right path. And one of the things before you do that is you may want to just consider a treatability study, just to kind of see where you're at and what kind of options you guys have, which will help you guide the process in your mind in regards to where you need to go.